Hi class. In today's video we're going to be talking about section 4.4, exponential and logarithmic equations. And so I'm going to start just kind of with a review of exponential and logarithmic functions, right? So that's where we take an input and then either apply an exponential or logarithmic operation to them, and then just kind of compare and contrast those, just to kind of remind us some of the properties of each of the types of functions. And then I will introduce a few more logarithmic rules, because we went over exponential rules and some logarithmic rules previously. But we have just a couple more we're going to need that we're going to use when we solve these equations. And so remember, an equation involves an equal sign and the assertion that two quantities are equal. So just for summarizing, and so on the left we have properties of exponential functions. Those are those functions of the form a to the x, where a is some positive number not equal to 1. And on the right we have properties of logarithmic functions, and that's where we have log of some arbitrary base a, where a is not equal to 1. And that function, remember, kind of undoes the exponent. It says what exponent must we raise a to get x. Now when we take the domain of our exponential function, it's all real numbers, so negative infinity to infinity, and it will give us a number between 0 and infinity as its output. Now remember, there's an asymptote there at 0, so we don't include the 0 in the range. And we already know from last time that logarithms are the inverses of exponentials. And so notice that the range of our exponential becomes the domain of our logarithm, and the domain of the exponential becomes its range. The intercepts, so we have a y-intercept at y equals 1. So when x equals 0, the exponential is equal to 1, and the exponential never crosses the x-axis, so there's no x-intercept. And then in our logarithm, because inverses are reflected across that line y equals x, there is no y-intercept because that's where our vertical asymptote is, but our x-intercept is at x equals 1. Because a, our base, to the 0th power gives us 1. So our asymptotes, like I just said, exponentials have one at the x-axis and logarithms at the y. And we know they're both 1-to-1 because they have inverses. But what that really means is if we have a to some exponent and a to another exponent, well, if those are equal, we can conclude that their exponents are equal. And the same for two logarithms. Log base a of u equals, and I'm missing log base a of v, if and only if u is equal to v. And then just properties of increasing or decreasing. But really, let's just look at a graph. So here on the left we have 5 to the x. So that's our general case where a is positive. As we move from left to right, our function is always increasing. As x goes to negative infinity, our function goes to 0. Whereas as x goes to infinity, our function goes to infinity. Now we consider to the 1/5. And notice that graph really just looks like 5 to the x reflected about the, sorry, I didn't mean to go forward. Let me see if I can go back. Trying to get my, there we go. Because if we would take this function here and rewrite it as 5 to the negative 1 to the x, well, that's 5 to the negative x. And so if we remember our help students, remember variables, this negative in front of the x means we reflect about the y-axis. And so that's why those are symmetric. And because they're symmetric, as we go to negative infinity, that function goes to infinity, but as we go to positive infinity, our function goes to 0. And similarly, we have our log base 5 of x and our log base 1/5 of x. And so this is showing you both have that vertical asymptote at x equals 0. Both of them cross the x-axis at x equals 1. But one of them, namely log base 5 of x, goes towards negative infinity as we approach 0 from the right. So remember that means log base 5 of x goes to negative infinity as x goes to 0 from the right. And it goes to infinity as x goes to infinity. And then log 1/5 of x goes to positive infinity as x goes from 0 to the right, and it goes to negative infinity as x goes to infinity. So we have some more rules of logarithms that we need to mention. So when we have the logarithm of a product, so right, we have the log of m times n, both inside the logarithm, we can split that into log a of m plus the log a of n. So multiplication inside the logarithm becomes addition outside. Relatedly, whenever we have a quotient, m over n, we get m minus n. So log base a of m minus log base a of n. And then we have our product, or our power rule. If we have log base a of some m to the rth power, so this is log base a of m to the r, maybe put parentheses around that, we can essentially bring this exponent down front, and we get r times the log of that number. On the slides that come, I'm actually going to keep these three properties up in the right corner because we're going to use them as we solve our equations. So for the first couple examples, we're going to look at exponential equations. So here it says, solve 3 to the 2x plus 5 equals 17. And just like when we were solving equations before, our goal is to find x. And so we can start by go ahead and we'll take the log of both sides. In this case, I used the common log base 10. You could have used log base 3, and that would have made the 3 cancel, but I just typically work with log or natural log because they're the most common. And then we can use our third rule up there in the corner, our power rule, to bring this exponent 2x plus 5 down to the front. And so now we have 2x plus 5 times the log of 3 is the log of 17. Now the log of 3 is just a number, and we know that the range, or at least log of 3, isn't 0. So we can divide that both sides by log 3. Now we have 2x plus 5 equals log 3, equals log 17 over log 3. Subtract that 5 over to the other side and divide by 2. And we get x equals log 17 over 2 log 3 minus 5 over 2. Now, thinking about your homework on MyMathLab, it might ask you to give a decimal to, say, 2 or 3 decimal places, and if so, just go ahead and type this into your calculator or GeoGebra, and it'll give you the decimal number. But generally speaking, I'm just going to leave them written like this, because this is the exact answer, and any decimal answer will necessarily be an approximation. So that one was straightforward. We had the logarithm, or the exponent, isolated from the beginning, and so we just took the log of both sides to undo it. Well, now this one's going to take a little bit more work. So go ahead and subtract that 4 from both sides. We get 3 times 5 to the x equals 7. We want that exponent alone, right? So our first step when solving exponential equations is work to isolate the exponent. Just like when we were solving radical equations, we would isolate the radical. Here we'll isolate our exponent. So we need to divide by 3, and we get 5 to the x equals 7/3. Now we can go ahead and take the log of both sides, and we'll be able to use our power rule then to bring that x down to the front. So we have x times log 5 over log 7/3. Now if you want, you could rewrite that log 7 over 3 as log 7 minus log 3, that's rule 2, and divide it by log 5. And so you either have log of 7/3 over log 5, or log 7 minus log 3 over log 5. For me, both are perfectly acceptable. The latter, log 7 minus log 3 all over log 5, is the most simplified, but they're both equally accurate. So here we have another one, right? And so you saw how that had a little bit more work in getting the exponent alone. Here we have 5 times 2 to the 2x plus 1 equals 7 times 3 to the x minus 1. So unlike our previous ones, we only have a single x, or where we had a single exponent, we now have 2 exponents. And so what we need to do here is get our exponents together. And so we have a couple ways we could do that, but we'll go ahead and take the log of both sides first. So take the log of both sides first, and you'll see why I chose to do that. You didn't have to. You could have divided that 3 with the exponent over, and divided that 5 over. But when we do this, we can use our first rule of logarithms and separate those products into sums, where we get log of 5 plus log of 2 to the 2x plus 1 equals log 7 plus log of 3 to the x minus 1. Then we can go ahead and apply our power rule twice. Where actually what I did here was I got both logs on the same side first, and then I applied the power rule. Again, you can do it in either way. I think doing it this way makes it easier to keep track of your signs. So what did I do in these steps? Let me get my pen out. So I took this log to this side, and I took this log of 5 to this side. So I had log of 2 to the 2x plus 1 minus log of 3 to the x minus 1 equals log 7 minus log 5. And then I was able to use my power rule twice on both of those exponents. What we do next is go ahead and distribute. So I distribute log 2 into both of those and log 3 into both of those. So we have 2x log 2 plus log 2 minus x log 3 plus log 3. And so we have a minus and a minus, which gives us a plus. Log 3 equals log 7 minus log 5. So now we're going to try to isolate our variable, our x. So go ahead and subtract that log 2 and add that log 3 to the other side. Right, so I moved this log and this log over. And now we can go ahead and factor this x out of both of those. So we have x times 2 log 2 minus log 3 equals log 7 minus log 5 minus log 2 minus log 3. Go ahead and divide that 2 log 2 minus log 3 over, and we're left with x equals log 7 minus log 5 minus log 2 minus log 3, all over 2 log 2 minus log 3. Now, yes, you could use your rules of logarithms, like we have up here in the corner. You might say, well, a log minus a log means we could divide. And so if you wanted, you could combine these. But again, I would say, unless it asks for a decimal approximation, just go ahead and leave it like that, because that's the exact answer. Here, let's look at another exponential equation. So here we have 3 to the x plus 5 times 3 to the negative x all over 3. And that equals 2. And so first, I don't like to work with fractions, so I multiplied both sides by 3 to get rid of my fraction. Well, and then I remembered that 3 to the negative x is the same as 1 over 3 to the x, so I rewrote that as 3 to the x plus 5 over 3 to the x equals 6. Again, I don't want to work with fractions, so if I multiply both sides by 3 to the x, so I have 3 to the x times the quantity 3 to the x plus 5 over 3 to the x equals 6 times 3 to the x. I can distribute that 3 to the x through, and I'll get 3 to the 2x, and I subtract that 6 times 3x to the left, and that 1 in the denominator cancels, so I both move this over here and cancel that 3 to the x. And now, to solve this, we're going to have to do one of our substitutions. So remember back when we were solving equations that were quadratic in form? And why I saw this was I saw a 3 to the 2x, let me get my pen, a 3 to the 2x and a 3 to the x, and then this one didn't have a 3 to the x term. So if you let u equals 3 to the x, we get u squared minus 6u plus 5 equals 0. Now this factors into u minus 5, u minus 1, because negative 5 times negative 1 is positive 5. But negative 5 plus negative 1 is negative 6. And that means that u is 1 and 5. But we don't really care what u is equal to. We care about what x is equal to. So we set 3 to the x equals both of those. 3 to the x equals 1, and 3 to the x equals 5. Well, what do we raise 3 to get 1? Well, we raise it to the 0th power, so that's x equals 0. And 3 to the x equals 5, well, we can use our definition of logarithms, and we're going to get log 5 over log 3. Or we can just take the log base 3 of both sides and get log base 3 of 5. And now, something that I haven't explicitly discussed, something called the change of base formula. Change of base. I said we could do this as log of 5 for log of 3. It turns out this log base 3 of 5 and this log of 5 over log 3 are equivalent. And we won't talk about why that's the case, but no, if you have some log and you want to change it to a different log, say log base 3, you just take the log of that number and divide it by the log of the base. No, that's a thing. I'm not going to test you on it, but you should know that it exists. Okay. So that ends our exponential equation solving. So let's work with logarithms a little bit. And I think in terms of the general process of sometimes you'll want to substitute, sometimes you'll factor, all of these things are relatively similar and straightforward compared with the exponentials. So what I did here, just like we want to isolate the exponential, we isolate the logarithm. I subtract 3 from both sides. And now, just like to undo an exponent, we take the log. Well, to undo a log, we use the exponent. And remember, if we don't specify the base of a logarithm, it's base 10. So we do 10 of 10 to the one side equals 10 to the other. And so 10 to the log of that something is just that something, 3x minus 4, where we use our power rule. Bring that down front, because log of 10 is 1. And then here, we have 10 to the negative 3, so that's 1/1000th. So what I said here is we know that 10 and the log are inverses, just because log of 10 is 1. So we could do that either way. 1 over 1000 is 0.001, because that's 1/1000th. Go ahead and add 4 to both sides, and divide by 3. You can put this in the calculator, but you're going to get a repeating decimal, and so I just leave it as a fraction. Now here we have log of x squared minus 6x plus 9 equals 0. So this is an instance where the log is already isolated. So we just raise both sides 10 to both sides. So we get 10 to the log of x squared minus 6x plus 9 equals 10 to the 0. Well, 10 and the log cancel out on the left. 10 to the 0 is 1. And so what we're left with is x squared minus 6x plus 9 equals 1. Go ahead and subtract that 1 over x squared minus 6x plus 8. Factor that 8 into negative 4 and negative 2. Negative 4 times negative 2 is positive 8, but they add to negative 6. Zero product principle tells us that then x equals 2 or 4. And something I haven't been doing, but we know is always worthwhile, is we can go ahead and substitute our answers in to make sure that we're correct. So if we have log of 4 squared minus 6 times 4 plus 9 we have log of 16 minus 24 plus 9. So that's log of 1. So this is 10 to what exponent equals 1? Well, that's 0. So we get 0 equals 0. And so we know that 4 is a solution. Go ahead and check 2. 2 squared minus 6 times 2 plus 9. We get 13 minus 12 is 1. And again, 10 to what is 1? Well, that's 0. Check. So it's always worthwhile, if you're going through, to go back and check your work. But often I won't require that unless it's something that you can write out by hand. So just like when we were working through our exponentials, we got to an example where we saw an example with 2 exponentials. Let's consider an example with 2 logarithms. So we have log base 2 of 3x minus 2 minus log base 2 of 5x plus 1 is equal to 3. And what we're going to want to do is we're going to want to use our second log rule, where we know that a log minus a log is just the log of that quotient. So we can combine that into log base 2 of 3x minus 2 over 5x plus 1, and that's equal to 3. And you might be like, well, why did I do that? Because now we only have one log to deal with. And that means when we raise 2 to both sides, because that's the base of our logarithm, we're going to get 2 to that mess equals 2 to the 3. Well, 2 to the log 2 is going to cancel out. So we'd be left with 3x minus 2 over 5x plus 1 is equal to 8, because that's 2 cubed. Now we can eliminate our fraction by multiplying both sides by 5x plus 1. Go ahead and distribute that 8 through and combine like terms. So here we have 3x minus 2 equals 40x plus 8. Combine like terms, negative 10 equals 37x. And x is negative 10 over 37. We have just one more example. Again, this one has multiple logs. But notice that they all have the same base. And that's important because we can't combine logs if they have different bases. But here we have log base 3 of x plus 1 plus log base 3 of 2x equals log base 3 of 3x plus 1. So we can go ahead and use our first log rule, where if we have the sum of 2 logs, it's really the product of the insides. So we can have log base 3 of 2x times x plus 1 equals log base 3 of 3x plus 1. Go ahead and subtract that log base 3 of 3x plus 1 over to the same side. And now we can use our second log rule, where we have a difference of logs, and divide the insides. So 2x times x plus 1 over 3x plus 1. That's equal to 0. If we want to eliminate that log base 3, we would raise 3 to both sides. So we have 3 to that mess equals 3 to the 0. Well, that means that inside 2x times x plus 1 all over 3x plus 1 is equal to 1. Eliminate our fraction by multiplying both sides by 3x plus 1. Combine our like terms by subtracting the 3x and the 1 to the left. I feel like I have a sign error, do I? So I have 2x squared plus 2x. Yeah, that should be minus 1. You can't even tell that's supposed to be a minus. So that should say 2x squared minus x minus 1 equals 0. So there, and I factored it correctly, so that's just a typo there. That should be minus 1. But then that factors into 2x plus 1 times x minus 1, because 1 times negative 1 is negative 1, but 2 times negative 1 plus 1 is negative 1. So that's factored correctly. And we get x is negative 1/2, or it equals 1. Now, that seems like a lot of work. And I want to point out that we could have started differently. Or not started, but from that second step. So here, at this second step, where we said log base 3 of 2x times x plus 1 is the same as log base 3 of 3x plus 1, we could have used the fact that our logarithms are 1 to 1, and this is why I reminded us of those properties on that second slide. Because we know if we have the log of u equal to the log of v, that those inside pieces are equal. So we can just immediately go to 2x squared plus 2x equals 3x plus 1. And notice that's that step there. And so we can still isolate it, and you can tell that I copy-pasted because I still have that typo. That should be -1, but it factors. And we get the same answer. And so see how many steps we saved by using that 1-to-1 fact. And so you can use 1-to-1 fact anytime you have an exponent, anytime you have a logarithm, and you have one equal to the other, you can assume the exponents are equal, or the inside of the logarithms are equal. So I think the biggest thing from this section is really thinking about what are our properties of exponents, what are our properties of logarithms. Like our negative exponents means it goes to the denominator. If we have the sum or difference of logs, it means we take the product or quotient of the insides in our power rule. And really thinking about the meaning of inverse. So if we have e to a natural log or 5 to a log base 5, those functions undo each other, and they return what's on the inside. And so those are the things I want you to keep in mind as you work on the homework from this section. Have a good day, everyone. I'll see you in the next video.